Right, hello, and thanks for having me. Thank you, all of you organizers, for putting this on. This is such a great idea of like two communities coming together and doing a crossover. I'm going to be talking about retiring React Native in favor of Rust. I thought, go hard or go home. But really, the title of the talk should probably have a question mark at the end, because it's not a story of having done it. It's a sort of a story of an experiment born out of a bit of frustration. And it's a frustration that is about all of this, right? It's the available options if I want to build a cross-platform app. It's 2023. These are sort of the options I've got. And I'm not going to go through the individual categories of things, like just have a look and browse. But I want to point out that there's a bit of a trade-off. If I want a native UX that behaves like the platform, like the user is expecting, I kind of have to suffer a little bit in the developer experience and testing experience and the effort that I put on. Or I can do it quickly and relatively cheaply and with a decent developer experience, but then the UX is not going to be that native because it's just sort of built once. And then there is a sort of a happy middle ground trade-off of React Native, which I'm highlighting just because half the audience is React Native. So that's what I'm kind of going to be comparing to. So none of them are a clear winner. And that trade-off is there. And I'm thinking, you're looking at that and thinking, well, that's just like your opinion. And you're right? Like before I get any deeper into this, I just want to say that this is my views based on my experience and what I've seen. Your mileage may vary. And if you're a fan of React Native and it's working for you, more power to you, it's great. There is no one answer, right? So yeah, keep doing React Native if it works for you. If any of this resonates, maybe I have some better ideas, maybe not. So I'm Victor. I'm a tech director at a consultancy called Red Badger. We are a consulting company. We work with our clients. We help them deliver digital products, apps, and websites, typically quite large and complicated ones. So we work with these sort of big teams building big products and seeing what it looks like at a moderate scale. I don't want to say at scale because that just sounds like Facebook, but at like reasonably moderate scale. And so that's the perspective I'm taking when I'm talking about these things. And yes, I'm a bit of a Rust fan, hence the fairies peeking out. Right, let's talk about React Native and what it did when it came out in 2015 and how that compares to the situation today. So when it first came out, it was just a massive win over what the native experience looked like. Right? It was cross-platform. It had a declarative user interface, which I think we can all agree is a better way of doing it by now, I hope. I hope that's not controversial anymore. It had better programming language, because Objective-C is just archaic and Java's not fun. And it had a developer experience of live reloading, whereas compiling the native apps just took forever. And I just find it really interesting that now in 2023, a lot of that has been eroded. Like the native platform have caught up. We've got declarative user interface toolkits in SwiftUI and Compose. We've got better programming languages, arguably better than TypeScript, but that's just me. And the live preview experience on both of those platforms also works. And all of those things have been designed to work together. So to an extent, other than the cross-platform part, it is maybe better on the native end, but you know, who wants to build things twice? So there is still just one way of getting decent native feeling experience without building it twice separately. So then what's the problem? I think it's this. From what I've seen and what we've seen at Red Badger and the various clients we work with, it is extremely hard to build a good React Native app, a good native feeling, fluid, responsive, native looking app. And so I kind of want to look at why it's so hard to do that and do that with quality and continuously, making sure that bugs don't creep in, that it doesn't slow down over time in terms of development velocity and how hard it is to actually maintain and change when there are these big teams working on it, sometimes multiple teams. So I kind of want to look at like a bit of, I don't know, theory, I guess. How do we ensure quality in building these things? And I think there are two parts to that. It's the language and tools that we're using, and then where they stop, we fill in the rest with automated testing. And I think both of those things have a room for improvement in React Native. And I kind of want to think about why and what you do about it. So starting with language and tools, that's the simpler one. These are all of the ways that the languages and tools we're using are helping us with quality. I can think of, there's probably more. Strict static typing, I think also no longer controversial. That is a good way of getting quality in. Linting and style checking. One interesting one, I think, is dependency management, a sort of software supply chain management, and making sure that the versions all work together and all the dependencies are declared and all of that sort of stuff. Test runners to run the tests and all of that sort of stuff. And there is an answer to all of that in React Native, right? It's those things. Problem I see is that they're also opt-in and add-on. So there is a limit to which they can actually be relied on, because all of them have been sort of bolted on to JavaScript and bolted onto the native ecosystem. So they necessarily have escape hatches because they have to be gradually introduced. And so your type checking is only as good as the nearest any type. And that's kind of true for a lot of them. You just can't quite have the confidence that they are there to catch you unless you're on a small team, a really good discipline that you can rely on and you just trust everyone, which is true up until about 20 engineers, 30 engineers. And then someone will just make a mistake and do it, and then everyone will do it. So there's a limit to what the tooling can guarantee, and that's where I think Rust can help. So I thought I would do a brief detour into Rust for the people in the room who are not familiar with it. Rust is all about strictness and explicitly stating your intent and safety and ensuring that things work the way you said they would. So starting with the language, it is a compiled language, statically typed language. It's got a really good type system for modeling data, which will be important later. So the example I've put on is modeling like a holiday sort of idea. You've got the start and end date, where you're going, and then the transport mode that you're taking. That I think is pretty familiar. What I really like about the Rust type system is the enums, where you can say the transport mode is one of these things. I'm either walking, and that's simple, or I'm taking a car, and then I need to know what route I'm taking, or I'm taking a train from a station with a departure time and a ticket, or I'm taking a flight. An airport is a different thing than a station, so I've got a different type for that. So the what's called variant of the enums can carry data, and those that data can be structs. It can also be enums, like further enum types. It just all nests. So you can model even a really complicated domain in these nested types, and it's all just data. The other thing that Rust does is generic types and traits so that you don't have to repeat yourself a lot. This, incidentally, is Rust's way of error handling. It's a result type, which is either OK, everything worked, or an error. If it's an OK, it's carrying some data, type T. If it's an error, it's carrying an error type, which is not any type. It's one that has a particular behavior called error. That's called a trait. So it lets you constrain what you're working on whilst staying generic. I'm not going to get any deeper into that because I don't have the time, but there are people in the room who can help you with that, and lots of documentation and books. The community is super helpful as one of the really nice things about Rust. Then moving on to running Rust, it's interesting for our purposes because it doesn't have any runtime. It doesn't have a garbage collector. It doesn't have like green thread runtime like Go. It's got like a predictable memory management system with a thing called borrow checker. That brings a lot of memory and thread safety. You can do async await. It's pretty like high-level APIs for all this sort of stuff. But not having a runtime makes it extremely portable. Like there are microcontrollers that run Rust, and it's actually a really nice experience running Rust on a microcontroller. If you want to get into embedded development, Rust is the way. And then finally, it's got a really good set of tools, where previously in the TypeScript slide, there was like 15 different tools on the slide. And Rust basically needs just one, kind of. It's called Cargo. It's its build and testing tool, its package manager, its tool installer and runner. The only other tool that a lot of people use is called Rust Analyzer, which gives you like live feedback in your IDE about types and lets you navigate and all that sort of stuff. So one or two, and everyone uses that. So you can sort of rely on that, which is really nice. So that's the end of the language side. I think it's really nice and you should give it a go. It's good fun, and it reduces your anxiety about code working. Like, I don't know about you, but in TypeScript code bases, I just keep feeling paranoid. Like, it says it will do a thing, but occasionally it doesn't. it betrays you. And you're like, well, what's the point of all of the type checking if I can't rely on it? Moving on to automated testing, where the tools stop, we need to supply some more logic to make sure that the thing we said would happen actually happens. And here I think is where we have even more room for improvement. And that's not specifically true for just React Native, it's true for other places. In my experience, testing React apps is hard work. We've seen teams who run CI pipelines with end-to-end tests that take 8 hours and more just to cover all of the behavior. It's slow, it's brittle, it's expensive. This is again my opinion, but I think it sucks. Testing React apps is just a pain. And I want to know why. What is behind it? Why has no one cracked it? And I think it's because we build them hard to test in the first place. And I've tried to put the finger on what it actually is, and I think it's this UI-centric architecture of React that actually does that, where the UI layout is the primary organizing principle of the whole code base, and then the behavior of what happens over time is secondary. So it's kind of like if you wanted to say it in a sentence, it looks like this, and when you poke it with your finger, it does that. And that leads to state management being sort of sprinkled around everywhere, and effects being directly executed from all over the place. When I say effects, I mean sort of anything that interacts with the outside world. So all input, output, disk, network, APIs, everything to do with time, random numbers, basically everything that in your tests you need to intercept, look at whether it's doing the thing that you want it to do, and stop from happening to make it repeatable. And all of that is, if I come back to this slide, all of that is sort of all over the place. So it's really hard to catch all of the instances of those things happening and say, this is what the state of the world looks like for my test so that I can express the expectations. This is I just put this in because I think it's really cool. Have you seen this thing? Who has seen this sort of thing, that kind of picture? Ooh, no one person. People call this the bed of nails. It's a sort of a testing harness for printed circuit boards. So these golden things down there, contact probes that touch the individual contacts on the PCBs and send signals and read the signals on the PCB to make sure that it's doing what it's supposed to do in every little place. Because if you did an outside-in test, like we end up doing with React apps, most of the time the result you'd get is the PCB just doesn't turn on. Something's broken, it doesn't power on. So I think that sort of how we give up and test things end-to-end from outside in is just a bit insane. No one does that with complicated things, and no one relies on it to that extent as we do with GUIs and React apps specifically. So is there a better way to build things so that we can test it better is the question that I want to try and answer. And I think the key to it is to start with the behavior instead of the look and feel. So I tried to say, what is behavior? If you boil it down and try to find the simplest, most generic explanation of what behavior is, this is what I came up with. User interaction causes an internal state update and some side effects. Or in type signatures, you've got a function that has some state, a kind of a model of your application state. It takes an event and it produces another state and a list of side effects. If I sort of cover off that half, that looks a lot like Redux, right, or Elm. So the effects are the sort of addition to this idea, and they express what you want to happen, and they take an event generically just because that's the sort of continuation. When the effect finishes, I want that event to be next, is kind of the idea there. So looking at the effects, I think the core thought there is that you're taking the intent of the effect and splitting it from the execution. Someone else will do that later on, some sort of runtime or platform or something. So as an example, in HTTP, the intent would be the URL that you're trying to send a request to and the request itself. The execution would be the process of doing a DNS lookup, TCP connection, sending some bytes, all that sort of stuff. So the calling of fetch in JavaScript is the execution. The request and the URL is the intent. And if you do that split, the benefit is you can skip that in test. You can just look at the description of the intent. That's a good thing for testing. And then it can be different on different platforms, which is a good thing for portability. So there's like a double win in there. And just to finish it off for the UI layout, this should sort of look familiar. That's kind of the React model, right? It's a function of some model that produces drawing instructions. Slight downside is drawing instructions are platform specific, so this is maybe more helpful. You go from model to some description, sort of agnostic description of what goes on screen, and then from that to the drawing instructions. And the second one can be platform specific. So to take that together, we end up with like a behavior-centric architecture where the behavior is primary, UI, layout, and information display is secondary. In other words, it does this, and it looks like that. And the interface of those things is data-oriented. They're pure functions. You can test those really easily. I provide the model and the event, look what comes out, is that the right thing? Good. So for getting out of the madness, I think we need better, safer, faster language with better tooling, and Rust seems like a good candidate, especially for the portability. And we need a better architecture for the portability and testability in that shape, or at least I want it to be in that shape. And so you kind of know what's coming, right? We built one, these guys in front and me. It's called Crux. It's a sort of we say headless app development, because you kind of build the apps inside out. It is really young. It's only like 6 months old. It's an experiment. We haven't really seen anyone use it in production, but we are desperate for feedback, so we want you to try it. It kind of looks like this. This is one view. You've got the middle green part is a core that is just logic, and it follows that pattern of those two type signatures. It's pure. It's just functions, and you write that once, and it's portable across various platforms. And then you've got shells around it that you can put it in, and those are platform specific. And they're responsible for the UI and also for executing the side effects that the core has requested. So those red things there are sort of different types of side effects that you can handle. They are sort of ports, and then each platform delivers an adapter. It's an old idea as well. It's called platforms and adapters, or hexagonal architecture. Dates back to at least 2005. We didn't invent that either. We just borrowed. Same as the Elm architecture that's inside. So none of this is new. We just put it together in Rust. Oh, right. One more point is that the Rust core has to be pure, because one of the platforms we target is WebAssembly. And that sandbox doesn't let us do any side effects anyway. So we have to maintain it pure. This like really, really simple app, which is pretending to be a payment terminal. So you put some numbers in. This is the like pretending to be Apple's new tap to pay capability. We can read cards on screen. So that sort of screen would come up. That's a placeholder. It's not real. Then you would go and tap your card. Some processing would happen. And you get a receipt screen. You put on hello@fake.com. Send yourself a receipt. And we're done. And we're back to the original flow. Really simple, right? So here is the sort of ideas that we've kind of already seen, starting with the events that can happen. It's an enum in Rust, and these are the actions the user can take. They can set the amount for the payment, they can start it, they can abort it, they can send it. Once it sent, we get an event that the send was confirmed. They can set the receipt email, send the receipt, then that gets confirmed, and then they complete the payment. So those are all of the sort of things that can happen. We've got a model, which at the moment has a payment which is optional. There might not be a payment in process. It's worth looking at the payment just for the sort of modeling. So payment has an amount, and it has a status. Where's that gone? There. Payment status is either new or pending tab or sent or completed with a receipt. Look at the receipt. Receipt has an email and a status again. That's down here. It's either new or pending or sent. And that's the whole sort of model of the state. There's a view model as well. That's what we're putting on screen. It's got a screen, which is an enum down here. And we currently support one screen, which is a payment with the payment that we've already seen. And then finally, for the effects, there's two what we call capabilities, the sort of adapters. One is render, which just tells the shell that there is new stuff to put on screen. And then there is a delay, which simulates all of that processing, because I'm not actually talking to payment APIs, but I could in the same way. I just didn't have the SDK or the entitlement from Apple or anything like that. So it's just fake delays. So let's look at one place where we use this. This is the update function. Actually, sorry, let me show you on here. So the update function gets the event and the current state of the model and the capabilities that it can talk to. And then it looks at what the event is, and based on what it is, it does stuff. It's like Redux. So in here, for instance, when we say send a payment, if there is a payment in the model, there is payment in progress, we say send it, which advances its own state. That's just mutating the model. And then we start a delay of 2.5 seconds. When that's done, we want confirm send to happen. Once confirm send happens, we update the state of the payment again. And the rest of it is really similar. The tests, I think, are really interesting because I have this basic happy path payment journey, which starts by making an app in this like testing harness. The only difference between running the app in this mode and the actual mode in real life is that we get access to the model, so we can set it to whatever we need it to be for the test. Otherwise, it behaves exactly the same. So we start by setting the amount to £10, it's in pence, looking at what the view is and making sure that it is. So assert equal screen is payment screen with that particular payment. If we send it, there is a new sort of assertion in there. We want to see back a delay. That's a request that we can eventually fulfill. So that's one. And also, we want to look at the view and make sure that it looks like what it needs to look like. And once this is simulating that the time has passed, we just resolve it. So we act as a shell for the app, right? We say time is up. Here is the request, just resolve it. That results in some events, specifically the one that we requested in the app. We send that, and we move on. So this happens instantly in the test. We're not actually waiting. Someone else will do that for us in the shell. And just to prove that to you, this is the unit tests for that. That took 5 milliseconds to run. It's just unit tests, right? It's fast. So that's the core, and it's worth looking at what the shellcode looks like just to like finish it off. So get ready to look at some Swift. So this is like the root of the app. There is some view, and it takes a core adapter. The core adapter is quite small. It does some serialization stuff that will eventually hide from you, but the principle is relatively simple. There's a view, which is a view model. This type is exported out of Rust and replicated in Swift, so you don't have to write that yourself. We've got tooling that just produces that for you. There is an update function and a process effect function, which is the sort of driving and driven side of the shell, right? So I can send an event in, and then stuff happens, and I process the requests that come back. The requests are requests for effects. So I look at that, and if it's a render, I'm just going to take the new state of the view model. If it's a delay, I'll service that in the way that Swift can do. Not particularly interesting if you're not a Swift engineer. And just to show you what the view looks like, it's like reasonably simple. This is Swift UI, probably somewhat unfamiliar, but hopefully readable. There's a view, it has a navigation stack. Inside of it is a switch, looks at the view screen. If it's a payment screen, it will put this input screen on with some navigation title and some other stuff. Input screen is this one with like a vertical stack, some spaces, buttons with 1, 2, 3. So it's just describing what goes on screen using the data that came from the core. So amount text is amount. And once I press one of those buttons, it does this insert number, which is called update. And then goes back to the core, sends a message into the Rust side of the thing. That services the state as we tested. So this is, I guess the point I'm trying to show is that this is really dumb. It's just projecting the state out and sending events back in. So there's not that much testing to do about this. There's probably a little bit, but not a whole lot. We were after building a bit more complicated demo. This is a note editing thing, so I can say, hello, React Native times Rust. I should probably zoom in, shouldn't I? The interesting thing about this is that underlying it is a, oh, sorry. Hey, what am I doing? is a CRDT, conflict-free replicated data type. So it synchronizes over message passing. So if I type into one, it appears in the other. If I select something in this one, go over there, delete, the selection sort of updates. It just synchronizes across, and it's messages. And I just want to look at real quick what the tests of that look like, because we can test the synchronization in unit tests in the same way that we did in the other thing. So this is an example of one of the synchronization tests. What I can do in the unit test is create 2 instances of the app in the unit test, because it's just a sort of data structure that runs some logic, right? So I make Alice and Bob, insert, Alice runs an update, inserts a world into her text document. We take Alice's edits, send them to Bob. Bob makes an update, inserts a hello. We take Bob's edits, send them to Alice. Alice does some typing, Bob does some typing, and then in the end, we look at Alice's view and Bob's view, make sure they look like what we expected and they're equal. And there's like 15 of those. And then I can run those too, just to show you that no magic is happening. If I do that, it will build. As it always does for some reason. 36 milliseconds. Right? It's just really instant because it's all unit tests. And that's kind of, I think, the point that I was trying to get to, is that you can do a lot of the end-to-end testing, even quite complicated, without having user interface, without having network, without having disk, without having all of this infrastructure around it, because what really matters is the logic of what you're doing, not the execution of the thing. So Crux is this attempt of building this sort of architecture for headless apps, if you will. You build them sort of from inside out. That node example is entirely test-driven. I started with the core, built the core to the tests, like feature by feature, and only after I built the user interface. And it makes testing just a lot easier. And you can run it pretty much anywhere, I think. Even Vision Pro, potentially. We'll see when we get one. And that's it. That's me. We really want your feedback. If you're willing to try this and you like it, give us a star. That's the repo. We've also written like a manual kind of book that you can read. Take pictures. And that's it from me. Thank you.
Sorry, it has been answered, but I didn't understand. So I write an app in Crux in Rust. So when I build iOS app, is everything converted to Swift, or is like business logic in Rust running on iOS?
Yes, the second. We compile it as a static library and link it into the iOS app, and there is like a message passing bridge between it and the user interface. So only the UI in Swift runs in Swift. It's not transpiled. It is running natively.
So I understand we need at least 4 languages: Rust, Swift, Kotlin, and let's say JavaScript. I don't understand your point of saying this makes testing easier, because you said React Native is difficult to test. I don't know from which point of view you are saying, but I see it as, okay, I'm a JavaScript developer. I have to learn 3 other languages, which I don't even have a clue how to test. So I don't think it's going to make testing easier. If you can explain about that, maybe you're seeing it as a company that has 3 teams, like if you can explain your point of view, but from my point of view, it does not make it easier, because at least I have to learn 3 more languages. And also, I don't see the point of using Rust at all, because I will write JavaScript, Swift, and Kotlin. But why should I even use Rust?
That's a completely fair point and a question I totally expected. Yes, this does mean you're going to have to learn a few more languages. The thing about them is, though, they are extremely similar. Like TypeScript, Rust, Swift, Kotlin, they're all so close together now. And also, what's hard, at least from my perspective, about learning the shell languages is knowing how to structure your app, knowing how to like do the various architectures, knowing the libraries, knowing all of these things. And you don't need almost any of that. You just need the UI toolkit. So in TypeScript, it's going to be React. You already know that. And then Swift UI and Compose are not as hard to learn as all of Kotlin and all of Android and all of iOS. So yes, I take your point. You have to learn a few more languages. But they are genuinely, they are not that different. If I managed, you will manage. But yes, it's a fair point. You need to learn more languages. And I guess on the simpler point, I mean more reliable, predictable, and way faster. So you can run them on your machine. You don't have to wait for CI for 2 hours. So it gets you there faster. So the time you spend learning the languages, you read back in how quickly you can then move. That's my perspective. But obviously, you can disagree.
Yeah, really fascinating stuff, especially like bringing the Elm and Redux stuff into Rust. If you're dealing with a lot of app state, especially in performance critical like UI stuff, how do you deal with the fact that message passing is not always going to happen when you want it and inside the frame budget?
So we haven't really looked at performance properly, and I'd really like to see examples of what that's like. For all of this sort of simpler stuff that we've been playing with, it was never a problem. It is really, really quick already, but I can see there's gonna be performance bottlenecks somewhere. It's really young. I don't have a good answer. Performance is gonna be something we need to sort out at one point.
Yeah, actually, I was building up on the same question. Essentially, you are trying to replicate the bridge which React Native is getting rid of, right?
In a way, they use JSON, we use Bing code. It should be faster than that, but yes, there is a similarity there. Yeah, performance is a bit of a question. Also, I guess one of the points I didn't say but wanted to make is that you don't necessarily need to use Rust or Crux to benefit from these architectures. You can probably do that in TypeScript just as well. Point I should have made and didn't.
And second is ChatGPT able to generate good Rust code?
You'd be surprised. It is actually like quite shockingly good at like when you write those tests that do that repetitive thing where you go move into this state and then this and that. It just auto-completes the whole thing. I have no idea how it does it. It's just...
As part of a JavaScript team, I assume that you're rewriting your sort of core stuff you used to do in JavaScript in Rust. And what's your experience with JavaScript? Because there's 20 years of experience there, and I guess you're doing it again from scratch.
Well, I think I would never argue to rewrite something from scratch as in bulk. I would probably introduce it gradually, like take a new piece of some really complicated functionality and start that. You can mount the core into just like an edge of the app and leave it to do a thing. My experience from going from JavaScript, then TypeScript into Rust is one of like relief is all I can describe it as. Like when Rust programs compile, I'm just like, okay, good, this is done. I don't worry, which is weird, right? It's not strictly speaking true. Like obviously logical bugs can happen, but the feeling is hard to describe. It's like, okay, cool, Rust's got my back. This will work. And it's like 99% of the time it's true. Unless I've said something completely dumb and it just does a different thing than I wanted.
And you're not trying to translate legacy JavaScript into Rust. You're doing it from scratch.
If so, I would do it gradually. But no, I'm not trying to. Yeah, come find me after if you've got more questions. I'm happy to chat.
On that as well, maybe before we finish, for the native React developers, you mentioned a phenomenal point. Like there's so many great fundamentals that I think have been embedded into the architecture that you guys have had by Rust, but it doesn't stop you from creating those boundaries yourself in your React Native app today. It's one of the things that we've been doing is defining very clear architecture. So all of the stuff that we do, I've seen it here, and it's great that it comes prepackaged into your framework. So kudos to you guys on that.
Yeah, all of that is replicable in TypeScript for sure. Thanks for that point.
Thank you.